Hi everyone, welcome to the second part in our Introduction to Macro Writing in ImageJ Fiji course. I'm Stephen Cross and I'm currently standing in for Dom, who actually prepared the material for this session. So in this session what we're going to do is we're going to build upon the concepts that we learned about in the first half, so things about variables, loops and so on, and actually start writing our own macros. We're going to ultimately end up with a single macro which will be able to take fluorescence microscopy images of nuclei and segment them, measure the distance for each nucleus to its nearest neighbour, allow us to potentially have some end-user control in the form of dialog boxes, and then output an overlay image which shows for each nucleus what was segmented and also the value for its distance, closest neighbour distance. Each of these 10 exercises is going to build upon this final macro. So for example, the first one is just using the macro recorder within ImageJ to extract out the different image processing commands that we need in order to segment the nuclei. Later exercises will look at defining our own functions within ImageJ to perform custom calculations. So this, for example, is that nuclei distance. Now, before we go any further, let me just show you where you can get all the data and examples from. So you can download all the materials for this session from our GitHub page, and there's a link to this in the description below. While this repository does include information that pertains to the first part of the course, the files here aren't particularly large, so what we're going to do is just download the whole lot for this session. So click the big green button up here and then go on Download Zip. Once you've extracted that out, you'll have a folder that looks like this. As I say, there's a few things in here that we can ignore. Things like the lecture macros folder is material from the first part of the course. The things that are of particular interest here are the example data folder, and we'll go through the individual components here in due course. There's the worksheet macros. So these are the model solutions which I will be working through after each section. But obviously feel free to look at them while you're working on the macros yourself. They might give you a bit of a leg up in terms of where you may be struggling. And then importantly, we've got this Word document here. And this actually outlines all of the different steps and all the different exercises. So the way Dom's formatted this is that for each of the exercises, you get a bit of background, a couple of key aims, some helpful tips, and later on you'll also see this syntax section which tells you any functions that you might need, or some of the functions you might need. Because of course you can just refer back to the ImageJ macros sort of cheat sheet here. This should list every single macro function that you can access. You can of course also use the macro recorder, and that indeed is what we're going to be seeing first time round. So the macro recorder will actually only give you anything that you can click on. So there will still be functions that you probably have to find by going to the online cheat sheet. So looking at this first exercise here, this is using the macro recorder. And what we're going to do here is we're going to take a fluorescent nuclear image. So that's this one here, nuclear stack 1. And you can see we've got the nuclei, and to anyone who attended the level 1 intro to ImageJ course, those images will look familiar. They're exactly the same images we used in that as we were working through the exercises. Unlike that, where we were getting you to evaluate different thresholds and filters, here we're just saying these are the best steps to use, or these are a set of example steps to use, should I say. So before we do that, I'm just going to show you how to run the macro recorder and also to set up a new script. So here's my copy of Fiji. So to set up a new script, to record a macro, just go to dev and record. If you're using plain ImageJ, I think you have to go to plugins, macros and record. It achieves the same thing though. It's just a shortcut within Fiji. If you want to create a new script from scratch rather than going via the macro recorder, you can click script here and then you have to select language as ImageJ1. At this point, if you want to pause the video, you can have a go at this exercise yourself and then resume the video once you want to see how I attempted it. So what we want to do is load in that example image and then start the macro recorder. So it's just going to go there. So the different steps that Dom's telling us to go through are load that, done that. Going to do a Z projection, so image stacks Z project, and it's in this case a max intensity projection. Then we're going to do rolling ball background subtraction with 20 pixel radius. So I'll change that. It says everything else is unticked. So you can see that that's removed that long length scale background. Now we'll go to image adjust and auto threshold. And we're going to use Otsu, quite standard, and then everything else unticked. So that's going to give us this image here. So indeed we see black nuclei on a white background. If we see the opposite, I'm going to edit and invert. Next we're going to fill in some of these holes here. So process, binary, fill holes, and you can see most of these now are solid nuclei. It's not perfect, but this isn't, or this exercise isn't so much about getting the perfect segmentation. It's more about just demonstrating the macro recorder. And indeed, as we're clicking through, you can see that these different commands are filling up here. So now we want to do watershed. So the purpose here is just splitting down things like that and this. So process, binary, watershed, and indeed it's done that one, but that wasn't sufficient for it to split that. But that's fine again, and those have split. Okay, so we need to go to Analyze and Set Measurements, and tick Area, Centroid, and Display Label. So display label here is useful because this is going to show the file name next to each measurement. For this particular analysis, or for this exercise, it's not so important because we know we're only processing nuclear stack 1. But later on in exercise 2, we're going to use the batch processor where we're going to run 2 or 3 different images. So being able to see which result came from which image is obviously vital. So click OK there. And now we're going to hit Analyze and Analyze Particles. And we'll set the size range from 50 to 500, show count masks, tick display results, and untick everything else. So we'll click that, and we get these two. And then we're going to just change that lookup table so that this is in that random color Glasby. So click Glasby. So each of the different nuclei here is just being assigned a different random color. At this point now we can just go to create in the macro recorder. So it's got all of our commands, and then that opens up in the scripting window that we saw a few minutes ago. We can save this file by going to File, Save As, and then if I just save that onto the desktop as x1.igm, and then you can see this. And it is just a plain text file. We could open this up in Notepad, for example, if we wanted to. Although with Notepad, of course, you lose some of the nice features such as this color highlighting and the autocomplete. So we can close all windows apart from the original Z stack and the script window. And then now get rid of that. So we've just got our original image and this. And now we can hit run, and what we should see is indeed we get our results table and that. And rather than taking, say, 20 seconds or so to click through, it's done it almost instantaneously. Okay, so now moving on to exercise 2, we're going to just use that same macro we've recorded, but apply it to multiple images. So the purpose of this would be if you were collecting images from, say, a high content system, where all the images are in the same format, and you want to apply exactly the same processing to them and just get a big table of results. So this one actually doesn't involve us writing any more code. It's literally just a case of applying the code in this exercise 1 macro to the folder of images. The folder in question is in this example data folder, and there's batch examples input, and you can see here we've got 3 stacks. So if I just load those in, they're different but all show the same thing. And then the original one, I think, yeah. As before, you can pause the video at this point and have a look at Dom's instructions in the worksheet, and this will explain how you can have a go at applying this batch processing to the macro you wrote in exercise 1. So what we want to do is go to Process, Batch and Macro, and then on the input here we specify our folder. So for me, batch input, and we also need to create an output folder, so I'm just going to put one in the same place, and I'll just call it batch examples output. And what's going to happen is when we put our macro code in here, it's going to identify all of these images in this input folder, and for each one sequentially it's going to apply the same macro, and then whatever image is active at the time, so the one currently selected, is going to be output to this output folder. So at the moment, of course, this folder is empty. So we do that, and then we just want to copy our code from there into here. So set the input, create an empty output folder, click open. Oh, so okay, so this is the other way of doing it, is click open here and then just select our code. Of course, that's just exactly the same thing. And then click process. And that really does, for this, take almost no time. So if we look in here now, we've got our 3 outputs. They've got the same name as their corresponding inputs, but each of those should be, that's it, a Glasby segmentation of that. And we've also got our results. So in this case, we were just measuring the area and XY centroid location of each nucleus. And here you can see that label column that we got by clicking display labels in the set measurements. So we know that all of these correspond to the first image, and then from here onwards to the second image, and then similarly from there onwards to the third image. And that's all there is to it. That is literally just running batch on your images. Now there are some special cases that's worth mentioning at this point. So if we go back and load in an image, doesn't matter what the image is, and load up the recorder again, certain operations, so if I take this image, duplicate it, and then say do add the two together. I mean, obviously in this case it's nonsense, but just for the sake of argument, we've added these 2 images together and created a new window. You'll see that the operation actually requires those image names. So anywhere where you've got an image name, what you'd have to do in your output macro is either rename them when they're active, so you can do that using the rename function, or you could use the get title function. So in here, I clicked create and it's generated that macro. So what I could do is im1 name equals get title, and then after duplicate, it's created that second copy, so that one will be active, and then I've got a reference to that second name. So this is just assigning a variable like we saw in the first half of the session. And then here, rather than having nuclei stack 1, we would literally just replace anywhere that it says that with im1 name. And similarly, this one, which corresponds to our second name, is im2 name. And then that we can delete. So now, if I run this, it still processes, and it will still process even if this changes its name. Rename. Run that, and now you can see that accordingly that one ends up being nuclei stack 1 renamed, and that's a result of. So that's just something to look out for when you are using the macro recorder, is whether or not there are explicit references to figure names. So for exercise 3, we're actually going to start building up a macro from scratch. So whereas before we were using the macro recorder to generate the code and then click the create button, and then that would populate the macro into the script editor, what we're going to do now is actually launch our own script. So file, new, script, as I showed you before, and then we're going to set the language to ImageJ1 macro. And in this case, we're going to use the classic first attempt at writing some code. So this is just printing a statement. Typically you would write something like hello world, or just a single piece of text, no variables or anything in there. And yeah, in this case, like I say, now we've got the syntax section of Dom's sheet here. So it tells us that the syntax we want to use is print, then brackets, then the string in there. So your string goes here, make it a good one. And then we'll just click run. So I'll give you a moment to do that, and then we'll come back and I'll show you how it runs. Okay, so what we're going to do is we've got this, it's already set up in ImageJ mode, so we can literally just start typing print. I'm going to go with hello world. That is the sort of traditional or classic thing to type under these circumstances. The purpose of this is, like Don puts here, it's basically just to introduce a couple of different concepts. It also gives you an idea of how easy it is to write code in a particular language. Things like Java, for example, would require another 4 or so lines in addition to this importing libraries and defining classes. Similarly, like Python, also you could do as a one line. An ImageJ macro is also a nice succinct language, doesn't require a lot of extra bits to run. So here we've got print hello world, click run, and then that just opens up the log window here and you can see hello world. And that's all there is to it. So now you've got an idea of how to form a basic macro in ImageJ, we're going to start increasing the complexity. And in exercise 4, what Dom's asking you to do is to determine if a number is odd or even. And to do this, we're going to start introducing, or in the process of doing this, we're going to introduce a few additional concepts. Again, things that we covered in the first part of this course. So these are loops, if and else, conditional statements, and then printing different statements depending on what the result was. The idea here, the aim, is to create a loop to iterate over the numbers 1 to 10, then add in a conditional statement which is checking whether or not that number is odd or even, and then depending on that result, printing whether that number is odd or even. So again, we've got the syntax section here. You can concatenate strings or link strings together using the plus. Again, this was covered in the first part. So here, print some words plus some of the words would literally just, well, we can demo that now. Some words plus some other words. If we run that, you can see it's just concatenated it into a single line of text. So that would be useful for saying this number is odd or that number is even, kind of thing. And the kind of key concept here, or additional bit, is this modulus operator. So this is the percentage sign. So what it's doing is it's saying what's the remainder after a division. So if you do 2 divided by 2, what do you get left over? Well, that's a complete division, so it comes to 0. Whereas if you did 3 divided by 2, 2 will go into 3 one time and leave a remainder of 1. So the answer from that would be 1. And by doing this, for 2, it's always going to be either 0 or 1. So if it's 0, you know it's an even number. If it's 1, you know it's an odd number. So that would be useful as something to include in your if statement. Then again, he's going through the syntax for loops. So this is something you've seen before. So the iterator start, iterator stop, and then how the iterator increments as it goes along. So the plus plus here is just adding 1 each time. And then after that, you have the double curly braces and the code that you want to execute on each iteration of this loop just goes in between there. It can be as small as a single line, or it could be, 1,000 lines of code. And then similarly, the format for the conditional statement follows a similar format. So you've got if, then the condition, curly braces for what executes if this is true, else if, and inside there as additional or an alternative situation, and then again inside curly braces. So if x was 1, this would execute. If it was 2, this would execute. Otherwise, what's between these, this would execute. So yeah, so again, I'll give you a chance to pause the video, and then when we resume, I'll go through one example solution to this. What I'm going to do now is start to build this up. The first thing we want to do is just to be able to iterate over the numbers 1 to 10. So for this, we use the for loop. As Dom shows here, you can use anything. You can call this anything. You can call this variable iterator. I'm just going to call it I, which again is a kind of normal value to use. So our start value is 1. I think that's what he said. Yeah, 1 to 10. Our stop value is going to be I is less than or equal to 10. And then on each iteration, we're going to increase this by 1. One of the ways that I like to prototype code is by just building it up piece by piece, rather than trying to type the entire thing, run it, and then not necessarily know where it's gone wrong. So for this, I'm just going to check that that works. So I'm just going to print the value of I on each loop, and what I should see is the values 1 through 10 being printed out in the log window. And indeed, that's what I see, so that's nice. I know that that loop is working correctly. The next thing I want to do is to determine whether or not a number is odd or even. So this is where we had this operator here. So I percentage assign 2, and we're going to assign this to a value. I'll call it remainder. So that, and again, always terminating lines with a semicolon, apart from the for and while and if and else lines, they don't need that, but any other command should end with a semicolon to tell ImageJ that that's the end of that particular command. So what I'm doing here is we've still got our loop. I'm printing out the number 1 to 10, and I'm also defining this new value remainder, which is just our current iteration divided by 2 and then getting the remainder. So I'm also going to print that value. So what it does is it alternates. So first off it's printing I, then the remainder. So 1 divided by 2 is incomplete, so the remainder is 1, then 2. 2 divided by 0 is 0, 3, 1. So what you should see is every other line will be our 1, 2, 3, 4, 5 as it's evaluating that. And then the alternate lines will be 0, 1, 0, 1, 0, 1, because that's an odd number, even number, odd number, even number. It's a little bit messy, so what we can do is now introduce that string concatenation. So for simplicity, all I'm going to do is have the iteration number, an underscore, and then the remainder. So now you can see 1 is 1, 2 is 0, 3 is 1, 4 is 0, 5 is 1, and so on. So again, 1 through 10, and then just oscillating between 1 and 0. So we know that the remainder part is working correctly. So I'm going to now introduce my if statement. So I go if remainder equals 0, then we know that that is an even number. So print is even. And of course we need to know what value is even. So now all I do is go I is even. And if I run that, we just get 2 is even, 4 is even, 6 is even, 8 is even, and 10 is even, but it doesn't know what it should do on the other circumstances where the remainder isn't equal to 0. And also if I put a space in there, that will format it a bit nicer. So what we could do here is we could either use an else if remainder equals 1, print I is odd, and that's totally fine. So I go 1 is odd, 2 is even, 3 is odd, 4 is even, and so on. But this is a little bit verbose because we know that if it isn't 0, it's going to be 1. So we can also just get away with an else. So if that's not true, always do this. And again, that just prints exactly the same thing. And that's all you need to do for that exercise. So at this point, you may be wondering how all of these different exercises will fit together. Just rest assured at this point that they will do later on. However, for now, we are going to continue looking at the individual practical components. So the next one we want to look at is effectively enhancing the functionality of our macro by introducing new calculations. So in this case, what we're going to do is we're going to take the previously identified nuclear coordinate centroid coordinates and calculate the distance between them. At this point, all we're doing is just taking the centroid coordinates for 2 detected nuclei and measuring the distance between those. In the next exercise, we'll extend this further by having a table full of nuclear centroids and calculating the distances between all of them, and for each nucleus determining which is the shortest distance. Since we know from the first couple of exercises that we're able to get out those results table with the XY coordinates, we're not going to use that at this point. We're just going to assume we've previously somehow acquired that data and load it in. So if you go to example data here and then just drag in this 2 nuclear centroids, we get what is effectively a results table with XY for 2 nuclei. One thing to note is that in order to get certain functions available within the macro, we need to rename this to results. So if you just go to File, Rename, and then call it Results, this allows ImageJ to know that this is, in fact, the results table, and you can see now that we've got this additional results column here. So what we want to do is to use this function here, again in DOM's syntax section. So we're going to assign a variable result, and that's from the function getResult. The first argument here is the string name of the column. So in this case, rather than being area, it would be X or Y, and then the row number, which I believe starts at 1. numbering starts at 1, I think. So yeah, so that's all there is to it, and then we get the xy for each of those. So effectively, you'll need to do 4 get results, getting result for the xy from the first row and the xy for the second row. Then we're going to calculate the distance between those 2 xy points, which, going back to a bit of classic Pythagoras, is x2 minus x1 squared plus y2 minus y1 squared, all square rooted. You can use, for doing the square, you can use this power function. So the first argument there is the value that you want to square, and then the second argument there is the power, in this case 2 for squaring. So this one here would be 3 to the power of 2, which is 9. And then also the other one you might need to use, or you will need to use, is the square root function, which again Dom gives you an example for there. So answer equals square root of 4 would of course be 2. So again, I will just give you a moment to pause the video, and then once we resume, I'll talk through one example solution for this. Okay, so let's say we've got our XY locations there, and we've got our script window. Let's open a new one. Then what we want to do is to use that get result function to get, first off, let's just get that first x value. So x1 equals get result, and with Fiji's autocomplete you can see, as I haven't actually mentioned before, that the code is being included there, and we know that the column number, the column name is just x, and it's row 1. And again, I'm just going to print that out so that we know it's worked. Run that, and it says, okay. So I said it starts at 0 and starts at 1. In fact, numbering here starts at 0. So our one column or our one row is 107. So actually, for the first one here, 0, and then run that, and now we should see that our result is printed out 166. And I'll just run that again. So 166.1152. So x1, y1, and then we'll do that for the second row. Let's do y2, and those from row 1, so row 0, row 1. And I could print all these together, so x1, put an underscore between them, y1, underscore x2, y2, run that, it's x1, y1, so 166 and 57, and then x2, y2, 107 and 81, which is correct. So those values are right. Now I want to calculate the distance between them. So first off, let's just calculate the difference between x values, for example. So dx is equal to x2 minus x1, and we'll square that. So in fact, before we do that, let's print it out. And then dx squared is what we'll call it, so dx2 is just pow dx2. And again, we'll print that. So we'll print dx, and then we'll print dx2. And that, so the difference between them is 58.8, and apparently that squared is 3,458. I mean, we could take that as being correct, but let's just double check it. So 58.8 times 58.8 equals, yeah, with rounding error, so that's correct. So that's cool. And what we can do, just for simplicity of not having that on the same line, is we could do it like that. So just replacing this with the actual expression. And again, if we just run that, it gives us that same number. So it's just saved us a line. Again, we could do that with y values. And that runs, and yeah, 545. No reason to believe that isn't correct. So now what we've done is x2 minus x1 squared, and y2 minus y1 squared. So what we want to do for the final distance is add those two together, dx squared plus dy squared, and square root the lot of them. So that was that square root function. Now if I print that, the distance between them is 62.3, which seems reasonable looking at the kind of magnitude of those numbers. And that's all we need to do for this exercise. So for exercise 6, what we're going to do is take the code from exercise 5 and start to extend it. So now, rather than comparing the distance between two nuclei, we're going to calculate the distance from that first nucleus to a whole load of different nuclei. And for each one, we're going to output the distance and then ultimately decide which is the nearest neighbour distance. So for this one, what's the distance to its closest neighbour? So like I say, we'll start with the macro there, and we'll also load in a new data set. So if you drag in this from the example data folder, it's similar to what you had before, and again I'll just rename it results. So similar to what we had before, the numbers are different, so don't worry that they were different from the ones when we're working with here. Basically, we're going to start with this one and compare the distance to every other row in this table. With those distances, we want to keep a record of what the minimum distance is, because that's our nearest neighbour distance, and it's that value at the end that we're going to print to the log table. So we're just going to say something like nearest neighbour distance equals 50, or whatever it comes out to be. So as before, feel free to pause the video now, work through this at your own pace, and then resume when you want to see how I work through this as an example solution. Starting with this, at the moment this will just compare these two, and indeed if we run that, you can see that currently the distance calculated between those is just shy of 80. What we want to do is keep this one the same, because we're, for now, for exercise 6, just going to compare this nucleus to all of the others. So we're going to put this inside a loop. So for I equals 0, I is less than, and I'll fill that in a second, I plus plus. We need to know how many rows we've got. So for this, n rows equals n results, and n results here is just a function within ImageJ. And in fact, we can print that out, n rows, and I'll just hide that. So using control and / just to comment out some code there that we're not wanting to evaluate at this point. So if I run that, it tells us there's 74 rows in this. And it's that value that I'm going to insert as the stop condition within our loop. So this is slightly different to the loop formation that we used for exercise 4, where we started at 1 and then went to less than or equal to 10. The reason for this is that you'll note that the getResult function is numbering starting at 0. So it makes it easier here that if we start at 0 and then stop when we're less than the number of rows, like immediately less than the number of rows, we're still iterated over 74 values, but we don't have to worry about subtracting off 1 every time we call the getResult function. So we're going to iterate over each of these rows, and rather than hard-coded pulling out the second row, which is number 1, I'm going to pull out number I. In fact, again, if we just comment this out and then look at those x2, y2 values that we're getting, print those, you can indeed see that we're iterating over every single row, so 30 and then 0.79, 110, 1.7, and so that looks correct. And then the last one here, 146, 244, 146, 244, so that's correct. Now you might notice that the first row that we will be comparing this value to is itself. So we want to avoid that because we don't want to be comparing, what's the distance of nucleus 1 to nucleus 1, because obviously the distance is going to be 0. So what we do is we put in a check here. So if I is equal to 0, and then we use the function continue. And what this does is, if this is true and therefore this executes, it skips the rest of this loop and goes straight back up here. So in our first iteration of this, when I is 0, we'll evaluate these, we'll get x2, y2, or in fact, to be fair, we could not even bother doing those, we can move it right to the top. So it'll just go I is 0, yeah, don't need to do any of this, go back to the top, that increments by 1, so now I is 1, this doesn't pass, so this fails, so we're able to execute all of this code. Long and short of it is that if we run this now, you'll see that the first value we get out is actually for the second row. It just means that we're not going to be comparing to herself. So now it's basically just the same as what we had before. We've got our x1, y1, we've got our x2, y2. This is going to change on each iteration of the loop, and we're going to calculate the distance, so dx squared, dy squared, square root both of those, and then print it out. And that is our distance between this and every other nucleus. And you can see that makes sense. A value there of just less than 80 is what we observed for those two a moment ago. Now the last thing we need to do in this exercise is keep track of which of these distances is the smallest. If we look through, we can see we've got 30 there. In fact, I think that 30 might be the smallest. So what you want to do is have a record of what the nearest neighbour distance is. One way of doing this is to define a new variable, which I will just semi-arbitrarily call nndist, and I'll set that to a very large number, which is, what's that, 1,000,000. And for each distance, we're going to compare it to this ongoing nndist value, and then we'll reassign that nndist value to the smaller of the two. So what I mean by that is nndist on each loop will be set as the min of, so that's just a function within ImageJ, min of the current nndist value, or d, which is our currently calculated distance between this nucleus and the others. And so what I'll do is I will print nndist and the current d value. So close that and run it again. And you can see here, so this is our currently calculated distance as before, so 79, 105, 30 and so on. And this is the current shortest distance or nearest neighbour distance. So on the first loop here, or the first iteration, well, technically the first iteration it skipped because it was I equals 0. On the second iteration, this million value got reassigned as 79.9 because of course 79.9 is smaller. Then on the next loop round, it calculated 105, which was larger than 79.9, so it stayed as the same value. Then on the next one, it calculated 30, reassigned it, and you can see that that 30 did indeed stay all the way to the end because no smaller value was observed. So at the end of this, we can just print nearest neighbor distance equals, and then nndist. And for neatness, I'll just get rid of that print statement there. So if I run that now, nearest neighbour distance equals 30.6745, and that's it. So what we're going to do for exercise 7 is continue on this same topic of calculating the nearest neighbour distance. However, whereas in exercise 5 we just calculated the distance between these two, and then exercise 6 it was the distance between this one and all of the others. We now want to calculate the distance between every single one of these and every other nucleus. So we've already got this one to these, then we also want to be able to automate this one to these, this one to these, and so on. In order to do this, you can use the concept of nested loops, which were covered towards the end of the first half of the course. And we're going to also, rather than keep printing out a bunch of nearest neighbour distances to the log window, we're actually going to set an additional column in the results table. So we're going to have, say, an nndist column here. As before, I'm going to give you a moment to pause the video, and then we'll resume and I'll talk through one of the solutions. We're going to start with the same code as last time, which if we just run again, yeah, that's still good, unsurprisingly. Now, rather than always hard-coded pulling out the 0 row here, what you want to be able to do is put this within an additional loop that 0 value increments each time. So this is your nested loop. So what I'll do is have an additional for loop here, which contains all of the previous code, and this one's going to run much the same way as this. J equals to 0, J is less than n rows, and J++, so incrementing by 1 each time. And because we're using that calculated value of n rows, that needs to go outside. So effectively what we're doing here is, this is still the same, this is all still the same as before, but rather than always having this hard-coded 0, we're going to have a value of j inserted in its place. So on the first iteration of this, j is going to be 0, as it was before. It's going to pull out x1, y1, so these two here, we're going to go through. We also want to now check, is I equal to j, rather than is it equal to 0. And that's it. So then we're going to calculate the number of rows, go here, j is equal to 0, pull out that first row, assign a new ridiculously large nearest neighbour distance, iterate over all of the other rows, check that the current count isn't equal to our j row that we're pulling out, so starting off with 0, calculate the distance, and then print. For now, we'll just print that to the log window. Then we're going to go back up to the top because this loop has iterated in like 74 times. Pop back up to the top. This is going to increment to 1. So at this point, we're going to be checking this row here. So that will be our x1, y1. Again, we assign for this row here, we want another large nearest neighbour distance because we're effectively calculating a new value. And again, we're going to iterate over all of these rows. In this instance, because now we're comparing I to j rather than I to 0, that first one, when I is equal to 0, is going to allow us to calculate that distance. So we will be comparing, now this is x1, y1, calculate the distance, and move on down the table, then j will go to 3 and so on, or j will go to 2. So let's just run that now, and what we should get is indeed this nearest neighbour distance equals, so for the first one here, the distance was 30.7, for this one here, it's telling us the distance is 24.02, and so on. So the last thing that we want to include is, rather than printing it to the log window, we're just going to use this syntax here to say set result. We're going to call it nndist, the original. Then the row that we want to put it on. So this is our current row here that we're iterating on, j, and it's the current value, so the nearest neighbour distance. Oops. And let's leave that, so then when we run this, you'll see it's both populated this row here, or this column here, and it's still printing this out to the log window. So yeah, we can see for that first row it's 30.67, which is the same as that. Second row it's 24.02, and so on, and all these values are the same. And so what DOM actually asked for was effectively that without the log window. Yeah, and again, that is done. So now we're able to take our results table and calculate the nearest neighbour for every single nucleus. The final components that we want to look at in terms of building up our final macro are dialog boxes. So these offer a way for an end user to interact with the macro without having to go into the code and edit values themselves. There are a couple of ways you can do this. The way we're going to focus on is the dialog dot notation. So this is like the original ImageJ way of providing dialog boxes. So effectively there's 3 components or 3 sections to creating a dialog box. You have this dialog.create, which actually creates the box in the first place. This section here, where you're populating it with the different parameters. So in Dom's question, or Dom's example here, he has a message which is some questions for you, which actually is just a non-interactive piece of text at the top of the box. Then the ability to type in a string, in this case, the question is warm bread or burnt toast. So what it would do is it would have that as the question, and then a text entry box where you could type either of those. Alternatively, you could add in a slider. So this, just a little slidey bar, which allows you to select numeric values in a particular predefined range. And then the third component here, or third element to creating a dialog box, is the dialog.show command. And it's at that point that the dialog box would actually appear to the end user and allow them to put in their values and then click OK. Once they've clicked OK, the code will then continue, and you can use these dialog.getString and dialog.getNumber commands to assign variables based on the values that were put in here. So with DOMs, like I say, he's put 3 elements into this. The first of these is non-interactive, so he's actually only got 2 that are going to return values. The first one's going to be a string because it's text, and the next one's going to be a number. And it's for that reason that his extraction code is variable1 equals dialog.getString, so that will just return whatever value the user had entered there, and then dialog.getNumber will return whatever value was shown in the slider. If you have multiple, say if you had multiple sliders within a dialog box, they come out in the same order that you put them in. So if you had 2 sliders, the first time you call dialog.getNumber will get the number for the first slider, and then the second time you call dialog.getNumber will get the value assigned with the second slider. For this example, what Dom's asking you to do is to provide 3 questions. One says, what day of the week is it? So Monday, Tuesday, Wednesday. What date is it? So, a value between 1 and 31. And what month is it? Then he wants the dialog box to be shown, and then when the users enter their bits and clicked OK, for the macro to extract those values and compile a string that says something like Wednesday the 14th of September. One thing to note here is the th there. Obviously, depending on the day of the month or the date, that will change. So you could go basic and just have it as Wednesday the 3rd of September, assuming that most things are th, or as an extension, you could actually try and use conditional statements or if statements to edit what value is being put in there, depending on whether it's first, like 1st, 21st, 31st, so have an st, or for the thirds, have an rd. It's up to you. I will actually cover both as example exercises. Again, this is the point where if you want to pause the video and have a go yourself, you can do, and I'll see you in a moment. First things first, let's just create a basic dialog. So we'll do dialog.create, and for this we're going to use, let's just put date question. And what we could do as most simple dialog here is literally just run that, check that it runs, and indeed we've created a dialog with the title date question that shows OK. Doesn't do anything else because we haven't asked it to put in any options. So the first thing we want it to do is what day of the week is it? So we'll have this as one where the user can type it. So it'll be dialog.add string day. In fact, let's just keep it succinct. Day of the week. And then we'll leave a blank section there. So when this gets displayed, it says day of the week and then somewhere where we can type. Now when I click OK, and effectively we're progressing from here, it doesn't do anything because I'm not extracting that value out. So let's do day equals, and now we do dialog.getString. So run that again, and I'll put Monday. Oh, actually, tough, I actually printed the result out. So let's run that again. Monday, and then to the log it prints out Monday. So we can see that's working. And just as a demonstration of this sort of first in, first out principle with regards to extracting out the same thing, so I'll put in date. I know Don wants this as a number, but just for the purpose of showing that they're both strings, so the first one that's going to come out will be the day, and the second one that comes out will be the date, and we will accordingly assign them day and date, and then show them like this. So let's mix things up and go Tuesday the 3rd. Okay, and you can say Tuesday the 3rd, so the first one that did come out was indeed the day. So that's cool. I'm going to delete that because what Don wants is for that one to be specified as a number, I believe. So in this case, it's .dialog add string date question mark, and in fact, let's do that as a slider. And with the slider, you actually input 3 values. So whereas with the string, it was just what's the default value. Here it's the minimum, the maximum, and the default position. So we know this is going to be between 1, 3, and let's just leave it as 1 for the default. And date equals dialog.get number. So day of the week, Monday, the 21st. That's Monday, 21st. And the last one we're going to do is to use a choice box. Add choice. So this is one that we haven't covered here. Nope. So in order to do this, what we're going to do is look at the ImageJ documentation. So one way you could do this is go add choice and then click on this, and it should indeed open up the ImageJ website. And you can see here it says label and items. Items is a string array containing the menu items. So add choice, and this is month. Choices, but we don't have this assigned yet, so this needs to be a string array. So if you remember back to the first part of this, choices equals new array, and we will define it as Jan, Feb. So what we'll do now is just run that, and you can see that those are the options, and I will cancel it because we've not yet defined how it's going to pull that out. So we will do month equals, and because this is a different type, it's actually .get choice month. So let's actually do today. So today is Friday the 21st. 21st, you can also type in there of May. And it is Friday 21st May. I mean, that's a very crude way of doing it, so I think more what Don was looking at or looking for is today's date is Monday the of, and remember to put in the spaces here so that they don't all get merged together. So Friday 21st. Today's date is Friday the 21 of May. So that's kind of like the simple answer. The more complex one would be now evaluating that date value and seeing, is it one of, you know, 1st, 21st or 31st. So what we'll do is we'll call it sup for superscript. Sup equals th. So most of them are going to be th, but what we're going to do is have a conditional statement in here. So it says if date equals 1 or date equals 21 or date equals 31, sup equals st. So here, if we redefine this as 21, now if we go, let's do something different, Monday the 1st of Jan. That should say today's date is Monday the 1st of Jan. If I go Monday 21st of Jan, alternatively if I do Monday the 4th of Jan, now it's 4th of Jan. Of course there are other things, so it could be Monday the 2nd and it will still tell me it's the 2nd. So what we want to do is add in an else if here. So else if date equals 2, 2nd, 22nd, or date equals 22, sup equals md, and date equals 3, or date equals 23 the 23rd, sup equals RD. I think that covers all the possibilities. So Monday, so 1st of Jan, I won't even bother writing anything in there. 2nd, 3rd, 4th, and then 5th should be the same. Now we can go to, say, 23rd, and so on. And that is it. In exercise 9, we're going to start combining in the different elements that we've seen through the first 8 exercises. In this case, it's the ability to record macros, or, well, the output from our recorded macro, and also the ability to create user interface elements through dialog boxes. As before, I'm going to give you a moment to pause the video, and then we'll resume and I'll talk through one of the solutions. So all we want to do at the moment is take our macro for segmenting out nuclei. So let's load in one of those example images here. And we want to start changing some of these parameters or via a dialog. So first thing we might change is the thresholding method. So for this, let's use a drop-down box, so one of those dialog.choice options, simply because there are only a finite number of thresholding options, and we don't want the user to start typing in random stuff, not knowing whether it's the name of a threshold. If we provide a list of thresholds, then they know that they're selecting a valid one. So if we actually just go to the threshold window here, we could type them all, but let's just go with Huang, ISO data, Li, and Otsu. So we'll do thresh choices equals new array, what did I say, Huang, ISO data, Li, and Otsu. And then we're going to create a new dialog dot create, and then this is segmentation. Choice, and this is threshold method, and it's thresh choices. And one thing we didn't cover last time is there is an optional third argument, which is the default value. So by default, it would just show the first one, which would be Huang. So in fact, let's do this now. So dialog.show, and then I'll just comment out these and run it. And you can see that it shows Huang as the default. However, what I could do here is type in one of the others, Otsu, and now Otsu shows as the default. An alternative way of doing this, in a neat way, because it sort of ensures that the default you're showing to the user is valid, is you could select it by index. So from this array, because that's just an array, 1, so this should show ISO data, because again, 0 indexing. Indeed, it shows ISO data. I'll do 3 because I want it to show Otsu, because Otsu is quite a good threshold. Another one we could do is filter choices. So if we go to process filters, we can see that all the filters end with ... So we'll just put in Gaussian blur and mean. That'll do. And like I say, we'll skip the ... because we'll add that in hard coded. Filter method. So let's add. For this one, we'll just go with Gaussian blur. Oh, in fact, there was also median. That's actually the one we used. So let's also add that as an option. And in fact, we'll default to that. So again, there we go, Otsu and median. Now we need to actually pull these back out. So thresh equals dialog.get choice, and filter equals dialog.get choice. And now I can uncomment this back out. And then wherever it would have had one of these hard-coded values, I just delete that and concatenate it with the value that we're getting out of here, which in this case would be either Huang, Isodata, Li, or Otsu. And we're going to pull out our filter value here, so that's dialog.getChoice. And if you're paying attention earlier on for the first exercise, based off Dom's instructions, you'll note that I actually missed out a step, which was incorporating a median filter in there, which kind of explains why my final segmentation looked a little bit noisy. Where are we? Exercise 9. So what I'll do is I'll open up the image and open up the recorder and just apply a filter, or in fact I'll duplicate it so we're not affecting our input, and then I'll just get the command for median filter for the stack, and then I'll insert that one in where it should have been there, so that's fine. So now we can replace this median value with our filter, so filter plus, and this is where I say I'm concatenating it with those 3 dots because all the filter values have that. So now we've got our raw image stack and we've got our macro. If we run this, Otsu and median, so this is actually the default values, we run that and it looks very tidy. Don't save. If we run it again, we could change this to Huang, and hard to tell, but that is a slightly different result. I should probably have left that open, it would have been easier to see. And what I'll do here instead is change that to Huang and have this as Gaussian blur. So if we compare those two, you'll see, for example, round here, they're slightly different results. Again, this lobe here has been removed, and so on. So you can see how this dialog box is now affecting the input for our macro. And so we come on to the final exercise, exercise number 10. With this one, we're going to continue the trend from exercise 9 of extending all of the bits we've seen in the previous exercises into a single macro. So in exercise 9, we introduced or we incorporated dialog boxes with the core segmentation code. Now in exercise 10, what we're going to do is introduce the code from exercises 5 through 8, which allowed us to measure the nearest neighbour distance for each of the nuclei. But of course that is just a case literally of copying and pasting in that code. So that's not hard enough for a final exercise. So the last bit that you're going to have to work on is introducing an overlay into the input image, or actually it's into the Glasby image. What this overlay is going to do is it's going to draw a piece of text, so draw a string onto your image, and that piece of information we want is the nearest neighbour distance, and we want it to be aligned on the centre of each nucleus. So effectively you look at the image, you see the centre of each detected nucleus, and there's a piece of text over it which says what its nearest neighbour distance is. This actually only takes a couple of commands. One is this overlay.drawString function. So information here is just your text. In this case, it's going to be your nearest neighbour distance. It's the XY position and the angle, so you could orient it. You can obviously play with that if you want, but I mean, I'm just going to leave mine as standard horizontal text. There's also overlay.show, so that's going to display the overlay once you've added all of the different components. Sorry, it's going to add that onto it. And you can also use the save as function to save your image to file if you want to. One thing particularly of note in the helpful tips here is this toUnscaled function. And this is because the centroid coordinates that you've got in your image, or in the results table you're going to get out, are calibrated. So they'll be in microns probably for this particular sample. As such, those distances are actually about half in absolute units what they need to be for setting the XY location, which needs to be set in pixels. So whereas, what I mean by that is, whereas your center for the nucleus might be pixel coordinates 300 x and 200 and y, your calibrated units might be like 100 and whatever the corresponding y value would be with maintaining that ratio. So what we need to do is to use this toUnscaled function, which will convert whatever you input as x and y into unscaled pixel coordinates. So for this last attempt, again, feel free to pause the video and we'll pick up and show you how to get these bits incorporated. Right, so what we want to do is find our code for measuring the distances, which was 537, sorry, not 538. So that's there. And we just plonk that on the end, and if we load in an image right now, nuclear stack 1, and then run this, we get the same options as last time. We run that, and you can see it's given us our results table with the nearest neighbour distance included in there for these. So that's the first part, that's great. And what we want to do is also incorporate this string. So first thing, let's use that to unscaled form. So we're going to introduce this at the end of each internal loop. So this is where for the current nucleus it's checked itself against every single other nucleus in that list. So to unscaled, and here it is the x and y coordinates of the active nucleus, as it were. So there, and then we're going to do overlay dot draw string, and that string is nndist, and it's x1 y1, and then overlay dot show. So now if we run this with those settings, you can see that it's done that. One thing that's not particularly nice about this is it's plonked it up in yellow. With that white background, it's quite difficult to see. So we can use a different command. I think it's something along the lines of set color. Yeah, set color, and we'll go 0, 0, 0, so it'll be black. And if we run this again, you can see now that that text has appeared in black. And that's it. You can play around with this a bit further if you want. There are additional overlay options. Overlay dots, there you go. You could, for example, draw a line between each nucleus and its nearest neighbour. Of course, for that to work, you would also need to keep track of which index the nearest neighbour is. So let's just do that just as a quick extension exercise. So if that would be nn equals, and we'll call it -1, because that is definitely not going to be valid index. And so for this we want to identify that if distance equals that, in fact let's call that nnx and nny. Rather than keeping the index, we'll actually keep the location of it. So if we have identified that the current one we're testing against is the nearest neighbour, we will also update nnx equals to x2, this value, and nny equals y2. And here we can do overlay dot, and we need to update those as well. nnx, nny, draw line, and then that's from x1, y1 to nnx, nny. And let's just see what that does. Boom. And indeed, you can see now that for a lot of these, where they're isolated, they're identifying each other as their nearest neighbour, but that's not necessarily true. So for example, with this one here, this one's identified the dark green one as its nearest neighbour, but for that dark green one, its nearest neighbour actually is this one here. So that's why if we zoom in on that, you can see that this one has a nearest neighbour distance of 16.9, but this one has a distance of 12.1, which indeed corresponds to this distance, because you can see that this one also has 12.1, so it's mutual like that. And that is it for this session. I hope you found it interesting and useful. If you do have any questions, you can contact us through any of these different routes. So we've got on the left our GitHub page, which you've hopefully already been to because that's where the material is. Same for our YouTube channel, and this is the facility website on the right. If you did find this interesting, please click like. Also maybe hit subscribe so you're notified when we do put up new videos. And thanks for watching.